My name is Arya Hakimian, and today we are taking a look at the thermal conductivity testing for building thermal mass performance in cement. We'll be hosting this webinar with some guests joining us from the University of Pennsylvania. On the call live here today, I'll be introducing some of our guest speakers, Yu Wang and Ziray Wang, who will be talking about some of the work being done in this space. This is also done in conjunction with the work with Dorita Aviv, PhD, and Shu Wang, the Professor of Engineering and Applied Science. So before we get started with I'd say the bulk of today's talk, just wanted to do a quick little introduction from C-Therm side. For those that may be new to us, want to give you a little breakdown of who we are and what we do. So C-Therm Technologies, we are a thermal conductivity instrumentation company specializing in the measurement technique in the transient space. So transient thermal conductivity characterization. Really our goal and purpose is simplifying thermal conductivity testing for the materials of tomorrow. So we do this through the advancements of transient techniques, and primarily just wanted to introduce our core instrument platform here, which is called Trident. So Trident, you can see on screen, this was an instrument developed with the idea of being modular in nature. There are 4 different methods available on this one system, really giving you the options to pick and choose the best tool for the task at hand. The idea behind Trident, really, this is a quote we like to make reference to, quite a famous one from Abraham Maslow. When all you have is a hammer, everything looks like a nail. So again, when it comes to the measurement of thermal conductivity, depending on whether it's the sample type that you're working with, the size that you have available, the conditions you're looking to test under, these can all essentially dictate which method is most appropriate, because there are certain scenarios where really choosing your method is going to be very important here in getting you the best possible data. So that's all from the Trident background. We won't go much further into that here today. I will just make reference, though, if you did want to maybe get a little bit more detail on some of the different methods that exist, how they compare to each other, what they're best used for, we do have a method selection guide. This was recently updated the other month. It's a really nice document, a free resource available for download, gives all kind of background on the methods that are available on Trident, as well as other methods for thermal conductivity that exist in the industry. So it gives you a nice kind of reference point to take a look at some of those different options, whether you're new to the space or just trying to maybe get some exposure on what other techniques exist. So that being said, that's, I'd say, the end of my intro here. Before I introduce our 2 guest speakers, I was given a quick video to share. So I'm going to play this just to maybe set up some of the discussion and the topic here today. So if you give me 1 second here, I'll get this up on screen and we'll get started. There, of course, will be technical difficulties. Let me get this trying one more time here. Sorry, folks. Okay, I think I might have got it here now.
Hi, I'm Dorita Aviv. I'm Assistant Professor of Architecture at the Weizmann School of Design, and I'm also a faculty member of the graduate group in Materials Science and Engineering. I direct the Thermal Architecture Lab, a cross-disciplinary laboratory that's at the intersection of architectural design, materials science, and thermodynamics. We look at potential synergies between materials, architectural forms, and energy flows, focusing on how they can impact human health and energy savings in buildings. So welcome to the lab. Here you can see how it can heat and cool people that are sitting on it. This is part of a modular shading canopy that has integrated into it of radiative and conductive cooling. This is a climate chamber where we test different components of buildings in full scale, simulating what it's like to be outdoors in real climates. Here is one of the concrete prototypes that we're testing in the chamber. We also use different types of sensors for both on-site evaluations and laboratory testing. Today you will hear from one of our PhD students, Ziray Wang, on our work with the Department of Energy on achieving carbon negative buildings through innovations in material applications to building materials.
I'm Shu Yang, a professor in the material science and engineering, and also the department chair. So my research covers a variety of the material science from, for example, soft matter, soft materials that will be used for soft robotics, actuators, shape morphing, to tuning the material's properties, such as changing the color, the transparency, and also going towards this carbon capturing to remove the carbon emission or reduce the carbon emission, and also going towards, for example, carbon absorbing concrete materials using the biomass integrated into our materials for enhancing the strengths and also carbon capturing. We also started to work on to, for example, removing the microplastics, PFAS, and critical minerals, as well as looking into how we go into work with the architects to design the sustainable buildings.
Awesome. So yeah, great little video there introducing some of the work that's being done in this space and kind of setting up the discussion for what's coming up next. So at this point, happy to introduce our guest speakers, Ziray Wang and Yu Wang, to take us through some of this content here today. So I'll pass it over to you guys.
Okay, thank you so much for the generous introduction and for having us showcasing the work we've been doing, collaborating between the School of Design and the School of Engineering and Applied Science at the University of Pennsylvania. My name is Ziray Wang. I'm a PhD candidate here at UPenn, and I also want to introduce our collaborator, Yu Wang from the Material Science Department. I have a presentation slide that I can share. So let me share my screen for a second. Hopefully this works. Okay. Well, hopefully everybody can see that. Perfect. Okay. Great. So the title of our webinar today is titled Thermal Conductivity Testing for Building Thermal Mass Performance and Emissional Saving. So again, this portion of the work is a collaboration between the Weizmann School of Design and Penn Engineering. My name is Ziray Wang, and then together here with my colleague Yu from the engineering department. So we saw the video, so you guys know about the lab and the kind of the work that we've been doing generally. Just gonna skip that. So we know that the buildings and building construction industry is actually account for a substantial amount of global greenhouse gas emission, right? So globally, that accounts for over 40%. About 27% of this comes from the operation of the buildings. That means the energy we use to heat and cool the buildings, to supply electricity to our equipment, and things like that. And then over 6 or 7% are related to the construction industry and to other construction related processes. So at the same time, due to the warming climate that we're living in, we project that there's going to be a substantial increase in electricity demand related to space cooling. In fact, that the space cooling demand is projected to triple by 2050. So one thing that we can do to moderate indoor temperature without reliance on mechanical system is through the use of building thermal mass. So building thermal mass is basically the fabric of building structures that is able to regulate and stabilize indoor temperature diurnally and seasonally. So for example, here what we see is how that works conceptually. On the left is the a temperature of the outdoor in red that swings between day and night. If you have a building that does not have a lot of thermal mass, the temperature curve will swing in a similar degrees of amplitude compared to the outdoor temperature. But however, if you have a thermally massive building, then the indoor temperature can be maintained in a much more comfortable range compared to a building that does not have a lot of thermal mass. So what does it do? So what does that mean? So it means that physically during the day, the thermal mass is able to absorb heat from the ambient and store it in its material cross-section. And at night, because of the outdoor air is cooler than the indoor air, then the heat will be quickly evacuated using ventilation, such as natural ventilation or even mechanical ventilation. So using building thermal mass has been kind of on the agenda and the radar of a lot of building science researchers, but also building policymakers. People have been recommending using building thermal mass to reduce the reliance on mechanical heating and cooling and improve the thermal resilience of our building stocks. But however, that building thermal mass, such as concrete, is actually quite substantial when it comes to its carbon footprint. We know that globally, concrete accounts for over 11% of the global greenhouse gas emission. So these are related to the material manufacturing, transportation of producing these kinds of building thermal mass materials. So what do we do, right? So here comes with the two research questions we're interested in addressing in this portion of our research. The first one is, can we design material thermal properties of a concrete to reduce the embodied emission related to material manufacturing while maintaining its thermal mass benefit for operational carbon emissions saving of buildings? And the second question we're asking ourselves is, can we improve the concrete thermal mass performance and operational emission saving of buildings by leveraging intelligent geometries? So it turns out we can. So we're very fortunate to be supported by a grant from the US Department of Energy Advanced Research Project Agency Energy program. So here is our entire DOE team, including principal investigator Dr. Masoud Akhtarzadeh, Dr. Shu Yang, Dr. Dorit Aviv, and other team members, where we collectively leveraging our respective expertise in civil, mechanical, control, building systems to reduce the emission of building structures. So to test our assumptions and to address our research questions, we collaborate with our colleagues to devise full-scale prototypes to see if the geometric factors are able to enhance thermal mass performance while reducing the emission related to the operational and embodied carbon of the buildings. So let's talk about the geometry factors. So what do we mean by that? So typically concrete building thermal mass, such as building floors, are made in these kinds of compact rectangular sections where a lot of the materials are buried within the cross-section and not exposed to the air. So, however, we with advanced digital manufacturing, such as robotic printing and structurally optimized floor systems, we can actually shape the cross-section and the overall geometry of building floor to use the same or even less amount of material, but then expose the material to the ambient air much more so. So it turned out that this will actually help us to reduce the daily indoor peak temperature substantially. So here what we see is that the blue is the ambient temperature of a typical day in a hot and dry climate in Tucson, Arizona in April. The red is the indoor temperature of a building where there's flat floor slabs, as we can see on the left. However, if we shape the slabs and expose its material to the ambient more so, we're able to reduce the temperature, the peak temperature, substantially, as we see in the green curve over here. So this is actually this is actually called a temperature damping. This is actually a metric we can non-dimensionalize and test and see how that will play out under different climate zones and different thermal conditions and different geometries we're able to test. So here is just to say that over a period of 24 hours, what is the temperature damping for the indoor air from the ambient temperature that is in blue here, right? So this is called the temperature damping factor, where we name that 1 minus A sub I. So it turned out that if we expose amount of surfaces and much more to the ambient air, while calibrating the thicknesses of the thermal mass, we're able to improve the temperature damping factors, right? So here is just to show the kind of the general principle is that as we increase the surface area in the x-axis, we are able to see a proportional increase in the temperature damping on the y. And if we're able to calibrate the thicknesses, then there is a substantial improvement in temperature damping, but obviously that you use a little bit more material. So the second thing that we're able to do is that we can design the recipe of the concrete itself to reduce emission, but also simultaneously maintaining the thermal properties necessary for thermal mass performance. So I'm going to pass the baton to my colleague, Dr. Yu Wang, to talk about the material recipe aspect of the work.
All right. Thank you, Zuri. So yeah, I'm mainly working on the material side of this project. So the main concept that we are trying to work on is we are trying to replace cement with a kind of low carbon, low cost sustainable material, which is we call it diatomic earth, we call it DE. So this material is not only like low carbon, low cost, is featured with nanopore structure as shown in the image in the slide. So with this nanopore structure, when we add it to concrete, it can assist the diffusion of CO2 in the concrete structure. So this is for the material. And then further, if we combine this material with the TPMS structure, which have a high surface area, so on the structure side, we can further reduce the structure weight and enhance the CO2 diffusion capacity on the structure side. So if we go to the next slide. Yeah, so basically this is our main recipe. We replace 30% cement with the DE. And for 3D printing concrete, since we do not have the cross aggregate, we only use fine aggregate as the aggregate. So which is we use the sand to binder ratio of 2:1. So we evaluating the CO2 uptake capacity of this this mixture, and we can see as the like 1 day, 3 day, 5 days, 7 days. I mean, first, no matter with DE or without DE, we can see a increased CO2 uptake capacity as the longer curing days. However, as we add DE, we can see a higher like CO2 uptake capacity compared to the mixture without DE. So where it shows the better like CO2 uptake performance, so when we use DE in the mixture. On the other hand, if we look at the other plot, which is the CO2 uptake rate with the depth of the sample, because typically for our traditional concrete block, it's the solid sample, solid block. So which means as we go into in depth of the sample, the CO2 diffusion capacity will be decreased, as shown in the plot. Without if we keep testing the sample that with the deeper on the deeper side of the sample, we can see a reduction of CO2 uptake. But when we add E in the sample, we can see a higher CO2 uptake on all across the depth of sample, which also highlights the CO2 diffusion capacity, which leads to a higher like depth of CO2 diffusion. If you the next slide. Yeah, so besides the material side, we also try to like further like studied on the structure side how we can use the TPMS structure to enhance the CO2 diffusion. So if we look at this, the top and bottom, there are two types of sample, which is the regular cast traditional concrete sample, which is a solid block. But so if we compare the CO2 diffusion past, which we define it as surface region and core region of the sample. For the traditional concrete sample, we can see a like reduction of the CO2 uptake capacity as we go inside in deep of the sample. But with the high surface area of the TPMS structure, we can see a more uniform CO2 diffusion because of the high surface area of the structure. So overall, like not only on the material side, also on the structure side, we use this structure to like enhance the CO2 uptake capacity. So if we go to the next slide. Yeah, besides CO2 diffusion, we can also, I mean, another thing is important is of course, the mechanical property. So we can get like by replacing cement with 30% of DE, we can get more than 25 megapascal compressive strength, which is even though it's slightly lower, but it's the reasonable range of regular concrete. So especially another like point I want to make is when we use high water to cement ratio because of the pore structure of the has stored the water, so it really effective on increasing the strength when a high water to cement ratio is needed, especially when we compare the sample with high water to cement ratio of 0.87, we can see a higher like compressive strength compared to the sample like without the. So overall is we can get a reasonable mechanical performance when we add DE to the sample. If we go to the next slide. Yeah. So beside that, because the other thing is interesting because the TPMS structure we use 3D printing method to print the TPMS structure. So we evaluate how the DE will influence the printability and buildability. So as you can see, after we add DE, we can get higher buildability layers, and also the DE leads to more uniform printability, which reduce the surface cracking in the sample. Sometimes we will absorb in the sample without DE, as shown on the right of the picture. So there's another point is that not only improve the CO2 uptake and we can maintain the mechanical performance. On the other side, is also really help us on the printability and the buildability. And then we further scale this up. If we go to the next slide. Yeah, we further scale this up using the robotic arm to like print TPMS structure in large scale, which in the meter scale. So we prove the scalability of this material by printing the meter scale structure, and we are now working on this like keep scaling this up. We are building like a floor system in the Innovation Center. So that's the ongoing work. Yeah, that's mainly the material side what I want to talk about. So I will hand back to Zuri to talk about the like thermal side.
Thank you so much. So we know that the custom concrete material recipe we devised is able to store carbon dioxide and bear potential in reducing the embodied carbon related to the material manufacturing while maintaining its material performance structurally. The second thing that we're interested in investigating is that with these recipes, can we still maintain the optimal thermal mass performance that bear potential in regulating indoor temperature and subsequently help us to save operational emissions related to the heating and cooling of buildings. So together with our material science colleagues, we devised a series of custom concrete material samples with biominerals, as we saw earlier, but also with other additives and replacement materials such as industrial mining wastes, and also testing these materials cured in different conditions, whether that's in high concentration CO2 or in the water moisture environment. So here are examples of these samples that we devised specifically to tailor towards the thermal conductivity and diffusivity testing that with the C-Therm machines. Here. So here is just kind of a quick videos showcasing a range of material samples that we're able to test here. And then with the help of the C-Therm instrument, we're able to robustly test the thermal properties of these samples with a high degree of precision. So here is kind of just a quick glimpse of what that looks like in our lab. And here is to show that kind of the range of conductivities and diffusivities related to the samples that we're able to test in our labs here. So what we're really interested in is that we want to kind of maintain or even enhance the thermal conductivity of the concrete material because that bear consequences in thermal mass performance, specifically the damping, indoor temperature damping factors that we described earlier. So here is what that might look like, right? So if we combine the material factors and geometry factors, we arrived at this design objective chart where on one hand, we want to expand the surface area exposure that can help with the carbon uptake, but also help with the thermal mass materials exposure to air to better damp the indoor extreme temperatures. On the y-axis here, that we also want to enhance or even increase the conductivity of the materials. So from a material science perspective, that it can work better as a thermal mass. So if we push sort of both of these design objectives, we're able to increase the damping factor to enhance the operational carbon emission savings that building thermal mass is able to give us. So one thing that we're also very interested in is to enhance the thermal diffusivities, specifically through the different material additives, also through the curing condition, as well as the density of the materials, as you can see here. So one thing that we're also very much interested in is to think about how we can bring material science sort of component scale testing analysis and to understand the implication of these materials from the perspective of buildings, not only in a specific sort of structural conditions, but rather in real conditions in different climate zones, in different cities, and also different future climates. So to do that, we use what is called a whole building energy simulation model. So this model does is that it'll take the operational schedules, the programs, the geometry, and as well as the building characteristics such as unit to wall ratios, the materials of building structure and building enclosure into a single numerical model to test the indoor thermal conditions as well as the energy use related to buildings such as heating, cooling equipment, so on and so forth. So with the thermal conductivity testing and diffusivity testings, we're able to use those results as input to our whole building energy models. So we understand how carbon absorbing concrete when used as building structure can enhance the performance of building in different climates and in different jurisdictions, as well as in different future climates. So here are just a series of figures where we see how the 3D printed structurally and thermally enhanced thermal mass looks like, and how that is being translated into a whole building energy model, as we can see over here. So that it accounts for not only the expanded geometry and surface area, but also the material properties that we're testing with the custom recipes. So with this set of tools from the bench scale material to a building scale model, where we see, for example, here in a typical summer day in the hot and dry climate of Tucson, Arizona, how different materials is able to behave in the real conditions, as you can see here, from normal weight concrete to different kinds of carbon absorbing recipes to a building with a light thermal mass with only acoustic tile, for example. So to conclude, our work, we devised custom concrete recipes, specifically designed with different thermal properties, including thermal conductivity and diffusivities. And we used the transient plane source TPS method to understand the material properties. We also discussed that the custom concrete recipes with carbon storage potential can reduce embodied carbon emission while simultaneously maintaining the optimal thermal properties for thermal mass performance and operational emission savings. Finally, we also discussed how we can expand surface area exposure with optimal thicknesses under a volumetric constraint can reduce both operational and embodied carbon emission related to the building lifespan. So we also want to acknowledge that research is really a kind of a social and collaborative process. We are very grateful for the support of the Department of Energy ARPA-E grant to enable our research between different disciplines and different fields, as you can see here. So thank you so much for your time, and thank you so much for C-Therm for the invitations. If you want to find out more about the work, so here the QR code leads us to our website, Thermal Architecture Lab, and also Shuyan Group of Engineering. We also left our emails here, should you be interested to reach out and discuss further. Thank you very much.
Awesome. Thank you very much to both of you for that presentation here today. So folks, just kind of wrapping things up, I'm going to go into a little bit of an outro to close out today's session. So bear with me for 1 second here. All right. So yeah, for the folks on the line, we do have plenty of resources available on the website if looking at, similar application focused content. Past webinars, our tech library is full of great examples similar to the content presented here today if you wanted to take a look at some of that. I will just make note of one of our webinars coming up next week. The final webinar this month in October will be a dynamic mechanical analysis or DMA focused webinar with a guest speaker, Dr. Richard Pazur, joining us to take a look at the DMA considerations in tire compounds. Also, coming up this, next month, in November, we will be at the Thermal Management Expo Europe. This is being held in Messe Stuttgart in Germany, November 11th to 13th. If you're planning to be in the area, we will certainly be in attendance. Happy to arrange a meetup or come and have a chat about your thermal conductivity testing needs. Also, today we focused a lot on the thermal conductivity side of things, but C-Therm, we do represent both Rigaku and Metrovib in North America for their line of thermal analysis and mechanical analysis testing, respectively. So there's other characterization needs that you have interest in. These are certainly discussions we are happy to have. Also wanted to make note of our thermal analysis labs group. This is our contract testing division here at C-Therm. So TAL offers all of the transient methods that are available on Trident, as well as other methods that exist in industry through testing services. So we're certainly happy to support those needs as well. If you'd like to learn more, we are certainly always available to set up a technical consultation. We do these daily. Gives you an opportunity as a user, someone interested in taking some of these measurements. We can guide you through the different application spaces, which methods are most appropriate for your materials, and give you a little showcase of how that all comes together. So certainly feel free to reach out in that context. And also, if you're just looking for some budgetary information for a quote, again, these are all things we're certainly happy to provide. You'll see some of these relevant links are being posted in the chat section by my colleague Carter, who's moderating today's session. I will point out our academic support program as well. So for folks from the academic sector, these are something that we have a standing program running for. If you are reaching out to us and are interested, if you're coming from academia, certainly make reference to this, and our team will be happy to follow up with some additional information. Lastly, give us a follow on LinkedIn. This is where we post all of our latest and greatest content. If you're looking to keep up to date with new webinars, blog pieces, technical resources, they all go to LinkedIn first. So definitely give us a follow on there. It's a great way to connect and keep up with what we're doing.